Welcome to Coaching Peeps. I go by the name Peeps, and in today's class, we're going to talk about buffer solutions, pH and pOH. Moving on, let's start with the definition of a buffer. A buffer is a solution of a weak acid and its conjugate base, which resists a change in pH when a base or an acid is added to it. Let's go over to the definition of a buffer system. A buffer system is a system that maintains the pH of the body. Okay, we have types of buffer system. We have the bicarbonate buffer system, we have the phosphate buffer system, and we have the hemoglobin buffer system. There are actually other types, but I'm going to focus on these three. So, a bicarbonate buffer system is the most important buffer system in the body, and it consists of the acid and its conjugate base. Let's take a look at this equation. Carbonic acid in a reversible reaction gives off hydrogen and bicarbonate. This buffer system occurs in the plasma. The buffer component, which is the acid and its conjugate base, is carbonic acid and bicarbonate. The buffer range is 6.4 to 8.4, that's the pH medium, and plasma is 7.4. So let's go over to phosphate buffer. A phosphate buffer consists of phosphoric acid and its conjugate base, and it occurs in the bone and the cytosol. The equation provided is dihydrogen phosphate ion will give off hydrogen and phosphoric acid. The buffer component is phosphoric acid and dihydrogen phosphate ion. The buffer range is around 7.0, while the pKa is 6.7. Please note that the buffer component is also known as the acid and its conjugate base. Alright, moving on to the hemoglobin buffer. It occurs in the red blood cells. In this buffer system, it consists of hemoglobin itself and its conjugate acid. The equation shows hemoglobin hydrogen ion plus oxygen in a reversible reaction will give you oxyhemoglobin plus hydrogen. And the pKa of this buffer is around 6.8 to 7.0. So the buffer component is hemoglobin hydrogen ion and oxyhemoglobin. Let's move over to Bohr's effect. Bohr's effect describes a decrease in hemoglobin's buffering capacity when it binds to oxygen in the lungs. Please note that the increase in the basicity of hemoglobin releases oxygen, while the increase in the acidity of hemoglobin binds oxygen. In summary, hemoglobin hydrogen ion plus oxygen in reversible reaction gives us oxyhemoglobin plus hydrogen. The oxygenated hemoglobin has the ability to bind hydrogen ion than oxygenated hemoglobin. Please take note. Also, an increase in the concentration of hydrogen ion favors an increase in oxygen binding, and vice versa. Lastly, Bohr's effect plays a vital role in maintaining acid-base balance in the body. Let's go over to the calculations on pH and pOH. Question 1. What is the pH of 2.0 times 10 to the power of minus 6 mole per liter of potassium oxide? So we're going to start off by listing the information given. From the question, we have the concentration of OH, which is the 2.0. We have the KW, which is 14, and the pH is unknown. So to find the pH, we are going to recall that KW equals pH plus pOH and vice versa. KW, which is 14, then also minus log K equals minus log H plus minus log OH, which is 1.0 times 10 to the power minus 14. To find the pOH equals minus log of OH, which is 5.69. So therefore, 14 equals pH plus 5.69, and the pH is equal to 8.31. Moving on, what is the pH of the solution whose hydroxide concentration is 4.0 times 10 to the power minus 4 mole per liter? Okay, we're going to start off with the information given, that is data given. The concentration of hydroxide is 4.0 times 10 to the power minus 4 mole per liter. Then KW, as usual, 14, pH unknown. So you recall pH plus pOH equals 14, and pH equals minus log of OH, which is 3.4. So pH plus 3.4 equals 14. Therefore, pH is equal to 10.6. Okay, calculate the pH of a monobasic strong acid with a concentration of 0.025 at 27 degrees Celsius. Okay, we're going to start off with the data given. Here, we're dealing with a monobasic acid, so that is one molecule of the acid. So therefore, 1 molecule of hydrogen concentration equals 0.025 mole per dm cube. To find the pH, it's minus log of hydrogen ion, which is 1.6. That's all. In case you're asked to find the pH of a dibasic strong acid, please multiply it by 2. That is 2 times 0.025. If it's tribasic, that is 3 times 0.025. Okay? Moving on, calculate the pH of 0.56 mol per dn cube aqueous solution of potassium hydroxide. So let's list the data given. We have the concentration of OH, which is 0.56, the pOH unknown, pH unknown, but the K is 14. So first of all, we're going to find the pOH, that's 0.25. Then recall pH plus pOH equals 14. Therefore, 14 equals pH plus 0.25. Therefore, your pH is 13.75. If you're finding me too fast, please kindly rewind, okay? So take note, an acid is said to be acidic if its pH value is less than 7. A base is said to be alkaline or basic if its pOH value is greater than 7, and a compound is said to be neutral if its value is equal to 7. So before you go, here are some questions to test your knowledge. Okay, 1. What do you understand by Bohr's effect? 2. Write down the equation, pKa, site of action, and the acid and its conjugate base for the following buffer systems. 1. Bicarbonate buffer system, and 2. Phosphate buffer system. 3. Define a buffer and a buffer system. 4. What is the pH of 2.0 times 10 to the power of minus 2 mol per liter of potassium hydroxide? And 5. Differentiate between the oxygenated hemoglobin and oxygenated hemoglobin. Okay? Okay, if you're finding any of these questions hard, please just drop a comment. I'll reply. Thank you for watching. Please don't forget to subscribe. I'll see you in our next class. Okay, thank you.